So let us try to solve this problem. How we are going to solve this problem, let us see. So we have an XOR gate like this, okay, and for one pin, one of the pin we have 1 and another pin we have X. So what is your output of this XOR gate? If you have this combination, what is the output of your XOR gate? Answer 1. Okay, so let us, yeah, so what is the output here, whether it is X or whether it is X bar? So whether it is X or whether it is X bar. So if you don't know, so you can solve like this: X bar into 1 plus X into 1 bar, that is X bar. Okay, so if one of the input of your XOR gate is 1, then output is X bar. Okay, now here you are going to get the output of your first OR gate is X bar. Okay, the output of your first OR gate is X bar, and if you are giving X and X bar to your XOR gate, you are going to get 1 or 0, you are going to get 1. Okay, now so on we have how many gates? 20 XOR gates. Okay, we cannot do for each and individual gates, right? So what we should do here, so we can take one analysis here. If we have one XOR gate, then we are going to get X bar as our output, and if we have two XOR gates, we are going to get 1 as our output. Okay, so for even number of gates, we are going to get 1 as our output if this is a connection, and for odd number of gates we are going to get X bar as our output. Okay, so since our number is 20, that is even number of gates we are having in a cascaded form, so we are going to get 1 as our answer. Okay, is this clear for everyone? So see this question, take 2 minutes of time, and we will discuss the solution. Okay, this is little bit time taking. We will discuss it. Parallelly, you can also try. Okay, parallelly you can also continue uh, trying. Okay, so we will see how to solve this particular question. So we have a input waveform. So the input waveform is, let me change the color. So we have a input waveform like this. This is 0 and this is logic 1. Okay, so we are getting a transition at time t naught. So at this particular time t naught, we are getting a transition from 0 to 1. Okay, and we have a circuit which is an XNOR gate, where your both the inputs are shorted, and here we are applying this particular waveform, and this output of your XNOR gate, sorry, it is NOR gate, and the output of your NOR gate is given to your XOR gate. Okay, the output of your NOR gate is given to your XOR gate, where you are going to get your output here V0, and this Vi is given to this G3 or G2. Okay, this is G2 and this is G1. Now what is saying that T1 is equal to T0 plus 10, that is time period T1 is equal to T0 plus 10. Okay, and time period T2 is nothing but T1 plus 10, and time period T3 is equal to T2 plus 10. Okay, so that is there is a 10 time unit difference between T0, T1, T2, T3. Okay, and they have also mentioned the delays. So the delay of your NOR gate is 10 nanosecond. This delay of your NOR gate is 10 nanosecond, and the delay of your XOR gate is nothing but 20 nanosecond. Okay, now anyone knows what is the name of this delay? What is the term we are going to use? So what is the name of the delay? Anyone knows what is the name of the delay which is known as? So this delay is known as propagation delay. Okay, this is known as your propagation delay. So in the logic gates, practically speaking, we will have this propagation delay. Okay, now yes. So now we should find our output. So we need to find our output. Now first of all, what I am going to do is I am going to get my out. I'm going to draw my output individually. So here I am applying Vi. So here I am going to get what is the output I am going to get here. Is this diagram correct? Yeah, Vi. So if I apply, let's say Vi is equal to 1 here. If I apply Vi is equal to 1 to this NOR gate, then 1 plus 1 is 1 and not is 0. Okay, if I am going to apply 1 here, then I am going to get 0, and if I am going to apply 0, then I am going to get 1. That is, this particular NOR gate is acting as a NOT gate. Okay, so this NOR gate is applying is working as a NOT gate. Okay, in the logic conversions also we have seen, right? If you are shorting 2 pins of your NOR gate, or if you are shorting 2 pins of your NAND gate, it is going to work as a NOT gate. Okay, so this is simply a NOT gate. Now this is an XOR gate. Now, so what we are going to do first is, here we need a complementary output. So I'm going to, let me add one more page. Yes. So what I'm going to do is, first let me draw the input waveform. This is my input waveform. Okay. So this is my input waveform, and this is time t is equal to 0, and at time t is equal to t naught, there is a transition from 0 to high. Okay. And let's say this is t naught, and this is t1, and this is t2, and this is t3, t4. Okay, the distance between this to this is 10 nanosecond, 10 nanosecond. Okay, yes. Now, so what is the output of your NOR gate? So let's say this output has some variable, let's say it is x. Okay, the output of this NOR gate, let us say, is at x. Okay, so how your x is going to look like? So the value of x will be, initially it is 0, right? So that's why it is 1. Now there is a positive transition at time t is equal to d naught. Whether this transition will be affected immediately at the output, whether this positive transition in the input will be reflected at the output at the same time, or where it will be reflected. Can anyone let me know in the chat box? Can anyone can see in the chat box? If there is a positive transition at t naught, then where we will get the output of the NOR gate? At which time we will get the output of your NOR gate? I'm just analyzing my NOR gate. Okay, leave everything. Just analyze your NOR gate. So if you are applying, if there is a positive transition at time t is equal to t naught, then where will be this transition reflected? So if there is a positive transition at t naught, where will be this transition reflected? At which time? Okay, so let me tell you. So if there is a positive transition at time t is equal to t naught, then what is the delay of your NOR gate? That is 10 nanosecond. So if there is any input transition at time t is equal to 0, then that particular transition, if it wants to be reflected at the output, then it will take 10 nanosecond. Okay, so that means if there is a positive transition here, then this particular transition will be reflected from 1 to 0 at time t is equal to t1. Okay, 10 nanoseconds after we will get our output. Okay, so this is your output of your NOR gate. If in the question they haven't specified this delay, then what is your output where you are going to get your output of your NOR gate? Exactly at time t not only you are going to get your output. But since they have given this delay, we are going to get our output of the NOR gate after 10 nanosecond NOR gate. Okay, now, so this output is given to your XOR gate, and one of the input is input only. Okay, one of the input of your XOR gate is direct input, and another input is output of your XOR gate, NOR gate. Okay, now, so what is your output of your XOR gate? It is just going to compare these two values. If they are different, then your output is 1, and if they are same, your output is equal to 0. And when you are going to get your output at same instance, or after how many nanoseconds you are going to get? So after 20 nanoseconds you are going to get your output. Immediate output you are not going to get. So if you are going to apply your input at t is equal to 0 time units, you are going to get your output at t is equal to 20 nanoseconds. Okay, after 20 nanoseconds delay, you are going to get your output. Okay, now how to get your output now? So at this particular instance, you are not going to get any output of your XOR gate. So initially your output of your XOR gate is 1. Okay, initially up to t naught, your output of your XOR gate is equal to 1. Okay, now at time t is equal to t naught, there is a change. At time t is equal to t naught, there is a change from 0 to 1. Now 1 XOR with 1 is equal to 0. So your XOR gate should be changed from 1 to 0, but it is, this change is not happening exactly at this particular point. No, it is not happening. So where is this change happening? So after 20 nanoseconds, this change is happening. So that is, this is 10 and this is 20. So here this change, this particular change is happening at this particular point. Okay. So 1 XOR with 1 is 0 now. So this change is happening after 20 nanoseconds because the delay of your XOR gate is 20. Okay. So it is becoming 0. Now what is 0 XOR with 1? It is 1. Okay. So that is, this change is happening. This is 10 nanoseconds now. So that's why 0 XOR with 1 is 1. So this is also happening after 10 nanoseconds only. Okay. So this is 0 for only 10 nanoseconds. Okay. Or else you can see like this. So this is T1, that is, it is 20 nanosecond. Okay. 20 plus 30, 40, that is 20 plus 20. After that is at 40 nanosecond, you can see another transition. Okay. So this is output of your, this is your output. Okay, I will explain this one also. Okay, this is a simple problem. So first of all, try to get your output expression x. Okay, so what is your expression x, which is nothing but a plus b bar the whole bar, okay, into b the whole bar. Okay, this is the expression we are getting. Now if I solve this, what I am getting, x is equal to a bar dot b into b the whole bar. That is nothing but a bar into b the whole bar. That is nothing but a plus b bar. So a plus b bar. So this is my output. Okay. So this is nothing but my output expression a plus b bar. So I need to perform this operation on my two waveforms. Okay. So I'm having b. Okay. So what is the first step I'm going to do? I'm going to perform b complement. Okay. So let me draw this waveform again. And this is my waveform b. Now how my waveform b is going to look like? For 5 nanoseconds it is going to be activated. Okay, so for 5 millisecond it is going to be activated and it is going to become 0 again. Okay, so this is 5 millisecond and again it is going to off and on, off and on, off and on, like this. So this is my waveform b. Now I need to perform b bar, b complement. So how my b complement is going to look like? So opposite to this waveform. Okay, so it is mirror for this waveform, mirror image. Okay, so this is your b bar. Now that's it, you need to add a and b bar, then you will get your final answer. Okay, so how your waveform is going to look like? So your a plus b bar, that is up to here, that is 10 plus 5 up to 15 milliseconds, your output will be 1, and after that, after 5 milliseconds, your output will be equal to 0. I'm going to see here. So up to here your value of b is 1, a is 1, and in this duration value of b is 0 but a is 1. A plus 1 plus 0 is 1 na? And here also a value is 0 and b value is 1. Okay, I will draw it again here so it will be clear. So this is my a. Okay, and what is my b bar? So b bar is high for half cycle and it is again 0, and again it is 1, and again it is 0, 1, 0, 1, 0, 1, 0. Okay, so this is my b bar. So what is the output expression I have got? A plus b bar. So just I'm going to add these two waveforms. So how my output, up to where my output will be 1, up to this particular point my output will be 1. Okay, So that is up to here it will be 1, because 1 plus 1 is 1, 1 plus 0 is 1, here also it is 1. Okay, so 1 plus 0 is 1 only now, and 0 plus 1 is also 1. Okay, and 0 plus 0 is 0, so it is becoming 0 at this point. Okay, and again it is becoming 1, and up to which point it is, this is 1 plus 1 is 1, and 1 plus 0 is 1, and 0 plus 1 is also 1. So total t is equal to 15 milliseconds it will be on. For 15 milliseconds it will be on, and for 5 milliseconds it will be off. And this is t is equal to 15 milliseconds. So this is your output waveform. Which of the following represents the correct waveform for X in the given circuit diagram? The waveforms are this one. Okay. So no need of options. Just try to solve this. You will get the answer. What is the output expression we are getting? What is the value of X we are getting? Can anyone tell me? What is the value of X we are getting? Exactly. That is A XNOR B. Am I right or wrong? A XNOR B. So this is nothing but your XNOR gate. So the whole circuit is nothing but your XNOR gate. Okay. So for your XNOR gate, if you are applying two inputs, if the two inputs are equal, what is your output? So this whole circuit can be replaced with an XNOR gate. Okay. So this whole circuit can be replaced with your XNOR gate. So this is nothing but your XNOR gate. And if you are giving A and B and your output Y, and if your A and B are equal, then what is your output? For your XOR gate, if you are giving two equal inputs, then what is your output of your X? Exactly. If inputs are equal, output is 1. And if inputs are not equal, then your output is equal to 0. So simply apply that particular law. So up to here, your output will be equal to 0, and it will be 1, and it will be 0. And okay, I will draw this. So at this point, the inputs are not equal, so your output will be equal to 0. Okay, the inputs are equal, so you are going to get 1, and the inputs are not equal, so you are going to get 0, and inputs are not equal, sorry, inputs are equal, so your output is going to get, and not equal, so that's why it is going to get 0, and these are equal, so that's why you are going to get 1, and not equal and equal. Okay, so this is the waveform you are going to get, and which is matching with option C. Yes, try this one. So a logic circuit and input waveforms are shown below. The output waveform is represented by, so they are asking for the output waveform. So take your time, solve this, and please let me know. So what is the expression X? What is the value of the expression X? What is the Boolean expression X we are getting here? Anyone solve this? So this is nothing but A bar plus B bar plus B whole bar. Okay, that is nothing but B plus B bar is 1. Okay, so A bar plus 1 the whole bar, that is nothing but 1 bar, which is nothing but 0, which is nothing but 0. So your output is nothing but 0. Option D. Everyone getting the same answer? So from the expression only we can get the answer. A bar plus B bar plus B the whole bar. B plus B bar is 1. So A bar plus 1 is 1. So 1 complement is 0. So your answer is 0. Yes. Next. Try this question. Exactly. So how to solve this question? So if we get any this type of questions, so we can analyze like this. So for this bulb to turn on, the mandatory condition is E should be on. Okay. Okay, E should be compulsory closed. And if your A is open or B is open, there is no mandatory condition that A should be closed and B should be closed compulsory. Okay, so how can we represent this condition, that is A plus B? That is A can be on, closed, or B can be closed. Any one is closed, and C should be closed. C can be closed, or D can be closed. Okay, so how to model this condition C plus D? and the mandatory condition is E should be closed definitely. Okay, so finally what we can do is A plus B into C plus D into E. Okay, so this is your output. Or else what you can do is, if the switches are in parallel, you can write plus operator, and these switches are parallel, so you can write plus operator. And if they are in series, you should write your dot operator. Okay, you can analyze like that, or else you can analyze logically. Next, try this one. Consider the given circuit of switching of light from two different switches. So the input condition needs to turn on the LEDs. Okay, so how to solve this? So this is same like your question which we have discussed on Saturday, I think Saturday or Friday. So how to get this? So here we have plus 5 volts, and for the diode should be to be turned on, we need 0 volts here. That is, we need 0 here. So for getting 0, it can be 1 0 or 0 1 combination. Any combination we can take. Okay. So let us assume 0 1 combination initially. Okay. Let us first let us try to take this 0 1 combination. That means if we want 0 here, your A value should be equal to 0 and B value should be equal to 0. And if your A value and B value are 0, then you are going to get 0 here. And if your A is connecting here, that is, it is A bar, that is 1, and B bar, it is 1, that is, you are going to get 1. Okay, so your output of your NOR gate is 0. Okay, satisfied. Now let us assume that your input of your NOR gate is 1 and 0. Okay, that means your output of your AND gate is 1 and this AND gate is 0. Okay, for getting the output of this AND gate to be 1, your input should be 1 and 1. Okay, that means this should be connected to 5 volts and 5 volts. And if these are connected to 5 volts and 5 volts, then input and then the output of your AND gate, that is, there is bubble, right? So that's why it is becoming 0 and 0, and output of your AND gate is 0. Okay, satisfied condition. So answer is, it may be A is equal to B is equal to 1 or A is equal to B is equal to 0. That is option D.